Now we have already seen that fluid deformation happens when there is a gradient in velocity, meaning that if this is a fluid element and if the velocity at one particular phase is larger than the velocity at another phase, then this element will deform. Let us now carry forward these ideas into strain and rotation rates. So we know that a fluid will deform continuously under the action of a force acting on it. And this is very much in line with what we have for solids. In the case of solids, the deformation becomes fixed, while in the case of fluids, the deformation is continuous, and hence we work with rates instead of deformation. So we work with deformation rates. Now, keeping in mind this particular idea of velocity gradient, let us go ahead and find out what the difference in velocity would be between 2 points. Let us consider a coordinate system like this, and equivalently we can write it as x1, x2 and x3. The velocity at this particular point is suppose u, and it is at a point x, and let the velocity at this point be u at x plus dx. Let us now decompose and write down this particular velocity in terms of this. So the u component of the velocity has three components: u, v, w. So it will have u, v and w. Similarly, it will have u, v and w. So u at x plus dx will be u at x plus del u del x dx plus del u del y dy plus del u del z dz and other higher order terms. And therefore, we can write the u component of velocity at x plus delta x, or rather dx, minus u at x to be equal to del u del x dx plus del u del y dy plus del u del z dz. Similarly, we can write the v component at x plus dx minus the v component at x as del v del x dx plus del v del y dy plus del v del z dz. And lastly, we can write down the w component of velocity at x plus dx minus w component of at x as del w del x dx plus del w del y dy plus del w del z dz. With this in mind, we can write everything in a short form notation. So du, which is the difference in the u component, which is this particular term, can be written as del ui, or rather del u del xi dxi, where we have used the Einstein summation notation. Just to recall, the Einstein summation notation means the index has repeated here, and thus there is an implied summation over all the indices 1 to 3, and this is del u del x1 dx1 plus del u del x2 dx2 plus del u del x3 dx3, where we've already said that x, y and z is equivalent to x1, x2 and x3, and hence this particular expression is the same as this particular expression. And so we can write it down in terms of this kind of a shorthand notation. Similarly, we can write down the same expression for dv as del v del xi dxi and dw as del w del xi dxi. Now once we have this, we can write this further in an even shorter form as dui is equal to del ui del xj dxj, where the repeated index is j and the dummy index is I. So j is the repeated index, means that j has to be summed, but I is the dummy index, meaning it can be chosen. So the meaning is, let me choose I equal to 1. So this expression reduces to du1 is equal to del u1 del xj dxj, and because we have the Einstein summation index notation, this will be del u1 del x1 dx1 plus del u1 del x2 dx2 plus del u1 del x3 dx3. Similarly, if I choose I equal to 2, I will have du2 is equal to del u2 del x1 dx1 plus del u2 del x2 dx2 plus del u3 del x3 dx3. And similarly, I can choose I equal to 3 and write down the same expression. And once again, du1 is equivalent to du, du2 is equivalent to dv, and du3 will be equivalent to dw, where u, v, w components of velocity are equivalently written as u1, u2 and u3 in order to write them in terms of indices. So we have dui, that is the change of the ith component of velocity, as del ui del xj dxj. Let us focus our attention on del ui del xj. This is an entity which contains two indices. The first index indicates the velocity direction or the velocity component, and the second index is the direction of the gradient, meaning del u del x is the rate of change of x velocity along x, del u del y is the rate of change of, or the rate of change of, is the spatial change of x velocity along x, del u del y is the spatial change of u velocity, that is this velocity, along y. Similarly, del v del x will be the spatial change of the of the v velocity along x, and del v del y will be the spatial change of the v velocity along y. So I've just shown 4 components, and you can easily extend this idea into the z component as well. Now because it is comprised of 2 indices, this particular entity is called as the rate of strain. Well, it's not the rate of strain, it's called as the velocity gradient tensor. This particular entity is called as the velocity gradient tensor. And if I write it down in terms of a matrix form, this will be del u1 del x1, del u1 del x2, del u1 del x3, and you get the idea. So this component will be del u3 del x. So I can write down this particular matrix in this particular entity in this kind of a matrix form as well. Now we can sort of perform some manipulation on the velocity gradient tensor. Del ui del xj can be written as half of del ui del xj plus del uj del xi plus half of del ui del xj minus del uj del xi. So this is a decomposition of that tensor in the form of a symmetric part and an antisymmetric part. And this expression is the same as writing a matrix A as half A plus A transpose plus half A minus A transpose. Now we call the symmetric part as Sij because so this is called as Sij and we represent this as half of Rij, where Sij is called as the rate of strain tensor. It's also sometimes called as the strain rate tensor. Similarly, Rij is called as the rotation tensor, and we will see why they are called as the rate of strain tensor and rotation tensor in what follows. But the important part is we can split the velocity gradient tensor into a symmetric form and an antisymmetric form, where the symmetric form sort of represents the rate of strain and the antisymmetric part represents the rotation rate. Why is it important for us to perform this particular decomposition? Rate of strain is associated with generation of stress because a rotating element, if an element simply rotates, it entails no stress, but a deforming element entails stress. So Sij, as we will see, would be responsible for the deformation of a fluid element, while Rij, as we will see, is responsible for the rotation of a fluid element. And as in solid mechanics, we want to relate the rate of deformation in the case of fluids with the stress induced in fluids. And so in order to form what we call as a constitutive relationship, we want to relate somehow the state of stress as a function of the local rate of strain tensor. And hence it is important for us to decompose the velocity gradient in terms of a symmetric and antisymmetric part. Okay, so any doubt in whatever we have done so far? Hello?
Sir, why are you not half factor is
It's
SIJ?
it's just a matter of convention. It's just a matter of convention, nothing else. Okay, so let's proceed. Let us now look at the interpretation of the various terms of Sij. Let us consider S11. S11 is half del u1 del x1 plus del u1 del x1, which is nothing but del u1 del x1. Let us consider a fluid element like this. Let us call it as A, B. And the velocity at point A is given as u1, the x velocity is u1, and the velocity at point B is going to be, so if the length of AB is delta x, then the velocity at this point will be u1 at x plus delta x, or equivalently it will be u1 at x plus del u1 del x, 1 times delta x. So this is using the Taylor series. So the velocity at point B, and we have done this in the previous steps as well, will be this. After a certain time interval delta t, this fluid element would move to the right. So let me draw it in a different color. And because the point B has a higher velocity than point A, it is going to stretch. So we are assuming a positive sign convention, and of course whether it will stretch or not will depend on the sign of this particular term. If this particular term is equal to 0, then points A and B will translate with the same velocity, and this element AB will not stretch at all. After a time delta t, let us say that the element ends up over here. This is A prime, this is B prime. Now the length of the element has changed. Let us call it delta x prime, and this is the situation after a time delta t. So if we focus our attention on point A, after a time delta t, point A will move a distance u1 times delta t. So this particular distance is u1 times delta t. After a time delta t, point B, which was initially over here, would move a distance equal to u1 plus del u1 upon del x 1 delta x times delta t. So if I were to find out the rate of change of the length of the element, fluid element AB, I would write it as, in the Lagrangian coordinate system, rate of change of length AB, but I am more interested in the relative rate of change, so divided by length of AB. So this will be limit delta t goes to 0, A prime B prime minus AB upon AB. Now what is A prime B prime going to be? It is going to be equal to, let us see what A prime B prime, it is going to be the coordinate of B prime minus the coordinate of A prime. What is the coordinate of B prime? It is, if I consider this to be the origin, it is the coordinate of B plus the shift from B to B prime. So B prime will be delta x plus u1 plus del u1 del x1 delta x times delta t minus the coordinate of A prime, and the coordinate of A prime is going to be u1 delta t with respect to this particular origin, of course. So A prime B prime is delta x plus, now u1 delta t will cancel with this u1 delta t, and we will be simply left with del u1 del x1 delta x delta t. Now we can recognize delta x to be the length of fluid element AB. So this is equal to AB. Let us write down the other term as well. Hence, A prime B prime minus AB will be del U1 del X1 delta X times delta T. And if I divide everything by the initial length, which is delta X, this particular term cancels out and I am left with del U1 del X1 times delta T. Lastly, I have to take the limit as delta T goes to 0. So 1 upon initial length d length dt. I am writing it in terms of d, but equivalently it can be written in terms of capital D. It makes no difference. It's just the Lagrangian derivative. But we have to recall that it is the length in the x direction. And so this will be equal to, oh, I have forgotten to write the delta t in the denominator. So it will be 1 upon delta t and the rate of change, because it is ddt. So finally it will be written as 1 over delta t times del u1 del x1 delta t, and the limit of this entire term going to 0. But delta t cancels out and we finally get del u1 del x1. So I had just forgotten to write down the limit 1 upon delta t. So it means the physical meaning of this is the rate of elongation of a fluid element in the x direction is going to be del u1 del x1. Now you can very well imagine that if I have a fluid element like this, the velocity at this point is v. Now the velocity at this particular point will be v plus del v del x2 dx2, and after a time delta t it would become something like this. If I call this a b and a prime b prime, point A would move a distance of v delta t, while point B would move a distance equal to v plus del v del x2 dx2 times delta t. So once again we can write down what the rate of change, so 1 upon length AB times the rate of change of length AB in the y direction is going to be. This will be equal to A prime B prime minus AB upon AB, this whole thing upon delta t, and the limit of delta t goes to 0. So this is the time derivative. And once again A prime B prime minus AB we can find out using this as the origin, and ultimately if you do the entire mathematics it will come out to be del v del x2, or more generally in an index form it will be del u2 del x2. That is, let us look at the physical meaning of this once again. del u1 del x1 is responsible for stretching in x direction. Why is del u1 del x2 not responsible for stretching in x direction? Because del u1 del x2 represents this particular gradient. So if I have a fluid element like this, then del u1 del x2 is sort of responsible for making this fluid element go something like this. But del u1 del x1 is sort of the difference in the velocity between this point and this point, and hence it leads to a stretching. Meaning if del u1 del x1 is larger than 0, it means that the velocity at this point is larger than the velocity at this point. If I call them as A and B, it means that the u velocity at B is larger than the u velocity at A, and hence B will move faster towards the right as compared to point A, and hence the length of the fluid element will increase, and hence this is the physical meaning of del u1 del x1 greater than 0. Similarly, del v del y or del u2 del x2 is like the differential in velocity between this point and this point. If del u2 del x2 is positive, it means that the velocity, the v velocity or the velocity in the y direction for point B is going to be larger than the y velocity for point A, and hence point B will stretch faster as compared to point A, and hence this entire length AB will stretch. Therefore, del u1 del x1, del u2 del x2, and del u3 del x3 are responsible for linear strains, or in this case linear strain rates, and they are the diagonal components of the rate of strain tensor or the velocity gradient tensor in general. So the diagonal components are responsible for linear strain rates, and you can easily show that these are also the diagonal components of the tensor Sij, because as we have seen, Sij is half del ui del xj plus del uj del xi, and if I choose I and j to be both 2, I simply have, for example, S22 equal to half del u2 del x2 plus del u2 del x2, and this is equal to simply del u2 del x2. Similarly, you can do the calculation for S33. Okay, any doubts so far? Any doubts on the interpretation of S11 S? Any doubts on the interpretation of S11, S22, and S33? Hello?
Sir, why did you take the Lagrangian derivative? Like, what is the difference between the Lagrangian derivative and the Riemann?
Because we are following the fluid element as it is deforming in the flow. Okay? In the limit delta t goes to 0, finally we are taking this limit. The Lagrangian and Eulerian coordinate become the same, and it is easier for us to appreciate physically if we track a given volume. So tracking a given volume is tantamount to doing a Lagrangian calculation, and hence that is called as a that is what I called as a Lagrangian derivative. But in the limit delta t goes to 0, both the approaches become the same. We've already covered this.
Okay.
Anyone else? So this is still not difficult to understand. Okay, so far whatever we are doing, it's still not difficult to understand. In fact, fluid mechanics is a very logical topic. There's going to be very few things That will be difficult to understand. That will come much later in the course.
Sir, will the value of S11 affect the value of S22?
Good question. And in fact, prima facie it will not, but the velocity fields UVW are not independent. It's a very good question. The velocity fields are not, each component is not independent of each other. They are bound often by an incompressibility constraint. And so if the velocity is constrained by this equation, one will often find that this is also constrained. And in fact, this particular expression is del u1 del x1 plus del u2 del x2 plus del u3 del x3, and it relates these three components because S11 is also, essentially you can recognize this as S11, you can recognize this as S22, you can recognize this as S33. So for incompressible flows, this will be equal to 0. It's a very observant question, I must say.
Okay.
They are not independent. Good. So anyone else wants to ask something? So if not, let us proceed to the next part, that is interpretation of the off diagonal terms. Okay. Uh, Let us now proceed towards an interpretation of the off diagonal terms of Sij. We've already seen that the diagonal terms of Sij, which are S11, S22, and S33, they are responsible for linear strain rates. Now, let us consider a fluid element as shown. Let the length of the fluid element in the x direction be delta x, length of the fluid element in the y direction be delta y. Let us consider that a velocity u1 acts in this point, and correspondingly the velocity at this particular point will be equal to u1 plus del u1 del x2 dx2, where again x2 is essentially y. So this is, if this is the velocity at this point, then obviously the velocity at this point we can cast as a Taylor series keeping x constant, and hence we will only have the y gradient over here. Similarly, the velocity over here, if it is u2, then the velocity at this particular point, that is a point where y coordinate is fixed, will be u2 plus del u2 del x1 delta x. Okay, so in this case del dx2 would have been simply delta y, or if I want to preserve our convention, it would be delta x2, where the length of this side is delta x2 and this is delta x1. Now because of these cross gradients in the velocity, let us consider what will happen. If I name these points as A, B and C, because there is a gradient in the y velocity across points A and C, point C will move faster in the y direction than point A, meaning after a certain time delta t, point A would move to this y coordinate and point C would move farther than point A in this coordinate. But because we are not considering any difference in the x velocity at points A and C, the distance between A and C in the x direction will be preserved. Okay, so this is going to be delta x1, and this difference arises because C has a higher velocity in the y direction than point A. Okay, now why have I drawn it slightly to the right? Because this entire cube is now facing a net velocity towards the right. So it means that point B will move further to the x direction than point A also. But the distance between points A and B in the y direction is still going to be delta x2. So point B will be somewhere over here, and the element will look something like this. I have drawn an exaggerated diagram because we are considering the difference in the entities after a time delta t, which is a small time, but exaggerating the diagram helps us in clearly demarcating the geometries, otherwise it will be all scribblish. Similarly, you can easily show that point D would be something like this. So it goes from being a square to a rhombus. Now let us analyze how we can sort of quantify this change of shape. Let us draw the initial orientations of C. If I call this C0, if I call this B0, let me call this particular angle as alpha. Let me call, or rather delta alpha, rather d alpha. Let me call this angle as d beta. Let us find out what the rate of change of that angle is. So we want to find out the rate of change of alpha, and we want to find out the rate of change of beta. Let us look at first rate of change of beta, because it is easier to see. It's a right angle triangle. So AC0 is a right angle triangle. Now what is the elevation of point A? Let us consider this level to be the origin, that is y equal to 0, not the origin but y equal to 0. So after a time delta t, point A has moved a distance of u2 delta t, whereas point C has moved a distance u2 plus del u2 del x1 delta x1 times delta t, and therefore the distance C0 is going to be the location of point C minus location of point C0, and because location of the y location of point C0 is the same as y location of point A, this is same as C y location minus A y location, and this is going to be equal to u2 plus del u2 del x1 delta x1 times delta t minus u2 times delta t, and this is equal to del u2 del x1 delta x1 delta t. Now tan of d beta is going to be cc0 upon ac0, and cc0 we've just found out, this is equal to del u2 del x1 delta x1 delta t, and ac0 is equal to the length of the side AC, which is 1 over delta x1. So delta x1 cancels out, and this tan beta is the tan d beta is thus del u2 del x1 times delta t. Now for small delta t's, that is small infinitesimal changes, we can write tan of d beta as d beta. We can take the delta t on the left hand side. So we have taken simultaneously the limit delta t tends to 0. So it becomes db dt. This becomes equal to del u2 del x1. So the interpretation of this is clear. The larger the gradient along x in the y velocity we will have, the larger will be the rate of change of the angle from the horizontal of this fluid element. If the velocity at point C in the y direction is larger than the velocity at point A, then point C will traverse a larger distance in the y direction, meaning I will have a larger d beta dt. If the velocity at point C is less as compared to the velocity at point A, then point C would have lagged and I would have a negative rate of change. Okay. So it is clear that the cross derivative is responsible for the alteration of a square element into a rhombus. Let us now look at what the rate of change of d alpha would be. So for that, let us look at this particular diagram once again. If it is clear, let me just quickly rub certain parts to make it slightly more clear. Okay. Now, after a time delta t, point A would travel a distance equal to u2 delta t, while point B, okay, so right now we are considering the other thing. So at the end of delta t, point A would traverse a distance in the x direction equal to u1 delta t, and point B would traverse a distance equal to this, which is equal to u1 plus del u1 del x2 delta x2 times delta t. Therefore, we can write down b naught as the difference in this and this. So this is equal to u1 plus del u1 del x1 delta t delta x2 times delta t minus u1 delta t. So if we were to write down tan of d alpha, let me just squeeze it somewhere over here. So tan of d alpha would be equal to bb naught divided by ab naught, but ab naught is the same length because we do not have any gradient in the y direction between points A and B. So this will be del x2. Okay, with this in mind, let us continue with the expression that we have just written. So tan of d alpha is equivalent to del u1 del x1 delta x2 delta t, because this particular term and this particular term cancel out from bb naught. This divided by ab naught, so ab naught is delta x2. Okay, and if we take the limit as this, okay, before doing the limit, let's go step by step. So this particular term will be equal to, so this delta x cancel out, and this will be del, this should be 2. So for small deformations, we can write d alpha, and if we take the limit delta t tends to 0 and take this delta t on the left hand side, so we obtain d alpha dt is equal to del u1 del x2. That is, if we have a line like this, if this particular point has a larger velocity as compared to this particular point, meaning if del u1 del x2 is positive, then we will have a rotation of this angle. This is what this means. So now let us write down an expression for the average change in the angle. So the average angle change will be equal to half d of alpha plus beta upon dt, and this will be half d alpha dt plus d beta dt, and this will be half del u1 del x2 plus del u2 del x1, and this is nothing but S12, and also it is equal to S21 because S is a symmetric matrix, the symmetric tensor. Okay. Similarly, you can do the same derivation for S23 and S13, and S23 will be equal to S32 and S13 will be equal to S31 also. Okay, any doubt in this so far?
Sir, doesn't the like the original dou u1 upon dou x2 give more information than the average that you take?
Which
Like
particular term? Wait.
like S like the Sij matrix, the octagonal terms,
Hmm.
they carry less information than we are getting an average here, right?
Hmm.
So we are getting an average of the deformation angle.
Hmm.
I mean the rate of change of angle.
Hmm.
But if we hadn't taken the average, you would have gotten more precise values, like more precise information.
But that
So
that precise information carries no weightage because when you try to relate stress, when you try to relate the stress and strain, okay, are you just talking about this half factor? Are you just worried about this half factor? Would you have been
no,
happy
sir,
if
I
this
am
half is not over there? So
like
you're talking
if
about
we had gotten
you're talking about these individual terms, right? This each individual term is carrying more information. You mean to say?
than the average.
Yeah. So the reason why it's not kept individual, it will be seen much later in the course, is because you need to necessarily take deformations of elements rather than the velocity gradients solely. That is, this combination of term will come into the definition of it will come into the relationship between stress and strain. It will never be a relationship between stress and del ui del x. Okay, because a velocity gradient term itself, it comprises of both the sort of deformation information and rotation information, and hence a sole term cannot be used to write down the relationship between stress and strain, in this case stress and rate of strain. Actually, this is a very important concept for continuum mechanics. There have been a large number of claims to have constitutive relationship between stress and something, but we cannot in fact even have a relationship between stress and the rotation tensor. This is also not possible. It must be some relationship between sigma and s, because s contains the information of deformation. Hence that combination of terms has to come. Actually, in tensor form, the velocity gradient is written something like this, and S, which is the symmetric part, is simply del V plus grad V transpose. So always constitutive relationships is in terms of this tensor. never in terms of this or this. Anyone else?
Hello, sir.
Yes.
Sir, if we consider this fluid element to be 3D, then what changes will come? Means three deformation angles will come into picture.
Yeah. So
So then how can you express at last in form of S?
why not?
So then how can we express the last equation of average deformation in terms of S?
So look,
Because
if
we will
you
get three terms, right?
yeah, so if you have three terms, then you take a projection of those angles onto one plane. And once you take a projection of those angles, see, 3 dimension, you will have three angles of the element. But
Yes, sir.
you don't want to complicate your life by taking three angles and then you have to project those angles onto one plane, find out those angles, then project back onto the other plane. So in order to avoid that, you take a combination of two velocities in one go. Meaning, if I were to write everything what we have defined so far, I could have taken a cubic element like this, right? But I would have kept all the velocities at all the points to be equal, so as to isolate the effects of del u1 del x2 and del u2 del x1. If you have a 3D deformation, you necessarily have to define that solid angle. It would become a solid angle or an angle in 3D in terms of two angles in two different planes. You can represent a 3D angle in terms of two projections. So instead of doing that, you just project everything, and projecting everything is tantamount to taking a constant velocity across all points. I did not want to
Okay,
discuss
sir.
this in the recording because unnecessarily it complicates things. So it's like saying that if this is 3D, this general angle, so it has two components. One is this component and one is this component. So you have to project onto this plane first, then you have to project everything onto this plane, and then you have to define the total angle. Is it fine what I'm trying to say?
Yes, sir, yes. But at last, whatever the equation that we will get, can we express the final form in terms of S? That's what I was asking. Means the final equation you defined as S12 or S21 in
Hmm.
previous derivation.
Hmm.
So in terms of 3D, will we able to use S at last?
It will be the exact same expression. It will be the exact same expression. Okay. We are simply decomposing it into all three different planes. So if you try to derive this, you will keep x velocity constant and take gradients in the y velocity and z velocity. If you try to derive this, you have to keep y velocity constant and take gradients in x and z velocity. So everything else will remain constant. This entire tensor represents all the different deformations of a fluid element in all dimensions. It is not restricted to any plane or something. But in order to derive what exactly is this contributing, this particular term contributes to the deformation of a square element in the xy plane and the angles between those elements. Is it clear? This
Yes.
this
Okay.
particular term will be responsible for the deformation of an imaginary element in which plane? It will be in the yz plane, and it will lead to this particular deformation, something like that. Okay.
Okay, sir. Okay, sir.
And this component will be equal to this component, this component will be equal to this component, this component will be equal to this component because of symmetry. All right.
Yes, sir.
Okay, let us proceed. Or you want to take a small break, 5-minute break? In fact, let's take a small break. I'm pausing the yeah. So let us proceed to understand the structure of the rotation tensor. let us again consider that same fluid element, and these as the angles. So we go with the sign convention that clockwise rotations are negative and anti-clockwise are positive. So the presence of a gradient in the x direction of the y velocity the presence of a gradient in the y velocity causes this particular element AB to rotate in the anti-clockwise direction. So if I look at the rotation rate, it is d beta dt, and this is going to be equal to del u2 del x1, and the presence of a gradient in the y direction of the u velocity, that is u1 velocity, gives rise to a rotation of this particular face, that is AC, in the clockwise direction. So from a velocity perspective, not just a rate of change of angle, but an angular velocity perspective, this rotation, despite it being equal to del u1 del x2, if I write down the net rotation rate, if I write down the average rotation rate, this average rotation rate will be half of d beta dt minus d alpha dt, and this minus sign precisely accounts for the difference in the direction of rotation, and thus this particular term becomes half of del u2 del x1 minus del u1 del x2. So it is like the rotation rate of this entire element. If d alpha dt were to be 0, then it's like how this element tries to rotate as a solid body. But apart from this, it also suffers a deformation, and we've already seen the expression for deformation. Let us write down the expression for the tensor Rij. It was half of del ui del xj minus del uj del xi. Let us write this down in terms of a matrix. So R matrix is, so what will be R11? It will be 0, because simply putting I equal to 1, j equal to 1 will cancel out both these terms. Similarly, R22 will be 0, R33 will be 0. This particular term, which is R12, is going to be whatever we have defined. Let us see the reason. So R12 is equal to half. It's not going to be the same. Let's see. So R12, you just put I equal to 2 and put rather I equal to 1 and j equal to 2. So R12 is half del u1 del x2 minus del u2 del x1. Okay. So this is R12. Let us write it in terms of the symbols over here. This will be R13. This will be R21, but R21 is going to be minus of R12, because R is an antisymmetric tensor. Similarly, this will be R23, this will be minus R23, this will be minus R13. We can define the vorticity of the flow field as the curl of the velocity vector. In fact, let us write it in terms of the old classical way before we go the symbolic way. Del x2, del x3, u1, u2, u3. So we see, let us write down the k component. The k component is going to be del u2 del x1 minus del u1 del x2. And the reason why I have chosen to write down the first component, the k component, is because our analysis of the rotation is in the xy plane. So if something is in the xy plane, the curl will be orthogonal to the xy plane. So we will get the z component of the vorticity. So the vorticity is given the symbol omega. So the z component of vorticity is having the gradients in the xy plane. Okay, whatever curl you take in the xy plane will give you the component in the z direction. So the k component is this, and if we compare this to the average rotation rate, the average rotation rate that we had just found out, let me copy it from here. Was this. So the vorticity is twice the average rotation rate. And it is all a matter of convention. Don't worry too much about the factor 2 and all that. But now, how can we write the vorticity? So obviously there is some relationship between vorticity and the tensor R, because R12, if you look, it is equal to minus of twice the vorticity, because the vorticity is equal to this term, rather it is minus half the vorticity. So this R12 becomes minus omega z, that is the z component of vorticity, upon 2, or equivalently I can write it as minus omega 3 upon 2. So there is some relationship that exists between the rotation tensor and the vorticity. Let us find that relationship out. So we have on one side Rij, which is a second order tensor, and we want to relate it with the vorticity. To map something with one index onto something with another index, why have I not written omega I or omega j over here? Because we have just seen that R12 is in terms of omega 3, because R12 involves the planar velocities in the x and y direction, and the curl in that plane would necessarily give me the vorticity in the k direction, in the 3 direction. That is why I must somehow separate out the indices. I must have Rij separate from the index of k, and the only way to do this is through the alternating tensor, and the expression is minus epsilon ijk omega k. Let us put down the values. Let us choose I equal to 1, j equal to 2, k equal to, so naturally k has to be 3, okay, because I equal to 1, j equal to 2 means in order to have a non-zero epsilon ijk, k must necessarily be 3. So let us write down that expression. So R12 is equal to minus epsilon 123 omega 3, and this becomes minus epsilon 1 2, so minus epsilon 123 is equal to 1, so this becomes equal to minus omega 3.
Sir, half.
Yeah, so half that factor I've forgotten. Hmm. So Rij, actually this Rij is not half of it. Okay, the very first mistake we did is over here. If you look back all the way up, well, now I have to record this again for the television thing. Anyway, if we go back all the way up, we have not categorically taken half into the expression. So Rij is simply this. Okay, so that gets rid of that half issue. So this is not half. All right. You can feel free to talk because it's that recording is anyway ruined. So
Sir, the most of that part is fine.
no. It's gonna be on telly, so I cannot I cannot afford to do that. I'll do the re-recording, no problem. I'll do it sometime peacefully at night. So anyway, so let us proceed. R12 is minus omega 3, so which checks out. Okay. Also the other components, if we choose I equal to 1, j equal to 2, and it doesn't matter what k is going to be because you have repeated one index. So R11 is going to be 0, R22 is going to be 0, R33 is also going to be 0. So in essence, we are able to relate the rotation tensor with the vorticity. Okay, I request you to do this calculation and compare it to the R12 values. So essentially, in the end, what do we have? The vorticity is sort of half, rather, vorticity, rather, average rotation rate is half the vorticity. That relationship is still true. So average rotation rate is still half the vorticity. That is still true. Okay. All that sign business needs to be done through this particular relationship. And the rationale behind writing it down in this kind of relationship is also clear, that swapping Ij leads to a minus sign, that is Rij is equal to minus Rji. So that the fact that swapping something gives us a reversal in sign also indicated that it has to be through an alternating tensor. It cannot be through any other means. Okay, is it clear?
Yes.
Okay.
So we should take a dot product vorticity.
Of
Uh, we did not we just considered a direction the k cap coefficient.
yeah.
Yeah. So vorticity is the whole I cap j cap k cap.
Yes. So this omega 1, 2, 3, these are the three components of vorticity. So the tensor is relating to each component of the vorticity. It is not the vector itself, it is just the component of the appropriate vorticity. Okay.
Okay.
So just for everyone to, I just want to tell this one last time. If you have a two-dimensional flow like this in the x and y plane, vorticity will only exist in the z direction. If you have a a flow in the yz plane, vorticity will only exist in the x direction, because you are taking a curl. A curl of a planar vector gives something which is orthogonal to that vector plane. Okay, that has nothing to do with the doubt someone just asked, but I'm just saying. So after vorticity, we come to what is an irrotational flow. An irrotational flow is something which has a zero vorticity. Okay, meaning that all the components of Rij, the rotation tensor will be zero. This is what is called as an irrotational flow, and this fact is tantamount to writing this: the curl of this is zero. And of course, we will consider this in slightly more detail in the later chapters. But from elementary vector identities, we know that if this is true, then u must be the gradient of some scalar. The curl of the gradient of some scalar is equal to 0. So in fact, if a flow is irrotational, I can equivalently write the irrotational flow in terms of a description of a scalar. But that comes later. But it is important for us to know certain relationships beforehand. The next important concept is that of fluid circulation. The circulation is defined as capital gamma. It is the integral of the velocity along a closed contour in the flow. So if we have a flow field which looks something like this, and if we can imagine a closed contour in the flow, then the circulation is, so if this element is ds along the contour, then I will take the u component at this point, I will project it on the boundary, that is u dot ds, and I will integrate it over the entire boundary. If the integral is 0, then we say that the flow has no circulation. Okay.
Also, are circulation and irrotational flow related? Like, if the flow is irrotational, then circulation would be zero.
Can you think of an identity which gives you something in terms of vorticity? Can you think of an identity which will convert this into vorticity? Yeah. So tell me what that Stokes theorem will be.
Del cross
It will be the integration of the curl
del
of
cross u
over
ds
over
dA dot n vector dA
dA.
dot n vector.
So essentially it is whatever I have the curve, this dA is over that entire area, and it is the vorticity, that is it is coming out of the plane. So this is the curl which is nabla cross u, and I will integrate it over the entire surface, and this direction will be along the normal of the area. So essentially it will not be this, it will be dot n. Okay, so this is essentially integral of omega dot n dA over the entire area of the closed circle. Is it clear? So I've used the Stokes theorem. Fine. Is this okay? Hello.
Yes, sir.
Okay. So I mean this pretty much wraps up this particular chapter. I will give the assignment by tonight. The assignment will also contain some other additional concepts. It will be framed in the form of a question. So yes, if no one has any questions, we can call it a session. I'll see you again on Wednesday.
How many questions will you give in the assignment?
Pardon me?
How many questions will you give in this assignment?
Something like 20-25.
Okay.
Arey, that's not a lot of questions.